Today we're going to shift to a new topic that's related, in at least in one way, to decipherability, and it involves strings. And this is a string matching problem. And string matching. And what I mean by this is that you're given a text, which is some string, a string of characters. And let me give an example. Well, you can really take any example. A, B, C, A, B, X, A, Z. Okay? Which is Superman's middle name or something. Anyway, if you follow those comics. And text, and then you have a pattern. For example, BCAA. And the question is to find all occurrences of the pattern. We usually call the text T and the pattern P. All the occurrences of P inside T. So in this example, BCAA occurs right there and nowhere else. So there's one occurrence. But in general, there could be several. Or there might be none. For example, if you had BAA, that's not in this pattern at all. So the general problem is you're given a text, you're given a pattern, and you want to find all the occurrences or determine that there aren't any. Now the pattern, well, the length of the pattern, we'll give that a name later, a symbol, but and same thing for the length of the text. Okay, so what's the primitive operation? Well, most of the algorithms that we're going to think about, and most of the algorithms that people have thought about for this problem, involve comparing individual characters in the pattern to individual characters in the text. So primitive is character comparison. And the other kinds of operations that are done in the algorithm tend to be fairly simple relative to the numbers of those, relative to the number of character comparisons. You have to spend some time in various algorithms deciding which characters you're going to compare and so on, but usually that's fairly, that work is small in relation to the actual character comparisons. So that's our primitive, and we'll be counting the number of character comparisons. So just pictorially, here's the text. The text tends to be very long in most applications compared to the length of the pattern. And I probably don't have to motivate this problem. I mean, how many people have solved this problem in practice? And I solve it, I don't mean you wrote an algorithm, but you actually did it today. Okay. None? You did, yeah. In what were you doing?
Well, I mean, like, there's all sorts of, like, word searches and word puzzles, for example, that kind of thing.
Word searches, word puzzles, but yeah, word searches are fairly common if you're using an editor and you're writing something and you're looking for some word in your text. That's an example of this. Or you're looking up something in on Wikipedia or whatever. Or I guess maybe I should have said, how many people have had this done for them today by something you used? Yeah, right. I mean, you use Google, you use whatever. It's ubiquitous. I just point that out because I think the first time I taught this, I don't know how many years ago, way before the internet, but I was introducing this problem, and somebody in class said, "Why would you ever want to solve that problem? I mean, what's that about?" It just seemed really strange. Even then, it seemed strange. But anyway, it seems like a very natural question. All right, so what's the most natural kind of algorithm you can think of for this? Here we have characters, and let's just say, well, that many characters in the text and that many characters in the pattern. And what is the most obvious way to look for occurrences of the pattern inside the text? Yeah.
Just take all added the original text that are the length of the pattern, you just match each single one.
Yeah, and basically, if I want to, you put it in a way that doesn't have a particular ordering to it, which is fine also, but let's just think of it this way. Suppose I put down the pattern first at the left end, then I would want to compare the first character in the pattern to the first character in the text. If they agree, then I move on to the next one. If they agree, then I move on to the next one. If I end up at the end of the pattern and all the characters have agreed or matched up to that point, then I found an occurrence of the pattern in the text. If they don't, if I get out, let's say, to the third character and it doesn't match, it mismatches, then I know that that's not a place where the pattern occurs in the text, and I can stop. I don't have to look further in the pattern for that occurrence. And then I move the pattern one place over, and I start again at the left end. Or I could start again at the right end, or I could look randomly, but ultimately I have to look at all the characters as long as they're matching, or stop the first time I find a mismatch. So the point is that in the most direct kind of way of doing this, you would place the pattern down basically at every possible starting position in the text, and then for that position, you would look at the characters in the pattern to see if they match the corresponding characters in the text. And that's, you could write that up very simply, and it's certainly correct. Okay, so this is the most naive algorithm, is place the pattern against the text in all possible places, and then for each one compare the characters in P to the corresponding characters in T until either a mismatch or all characters match. And again, if you put the pattern down in a place where all characters match, then that's certainly an occurrence of the pattern inside the text. Otherwise, it's not an occurrence. And if you've covered all the possible starting places, at the end it's just that one, then you've certainly found all the occurrences of the pattern inside the text. Now, if the number of individual character comparisons is our measure of complexity, what's the worst case running time of this algorithm? Or a bound on the worst case running, yeah.
It's almost the length of the text multiplied by the length of the pattern?
Yeah, that's even more precise than when we need to be. It's just, all I had in mind was just the length of the pattern times the length of the text. Basically, the number of places you can put down the pattern is bounded by the length of the text. And when you've done that, for each place you put it down, the work you do, a number of comparisons, is bounded by the length of the pattern. Okay, so this is certainly an upper bound. What was suggested here is we could be a little more precise. The number of places you can put down the pattern is the length of the text minus the length of the pattern, because at the end, you can only put it in that one position. If you push it beyond there, it's not possibly a match. But the length of the text is usually assumed to be very large in comparison to the length of the pattern, so that small modification doesn't change things. And then if we say that for every time you put down a pattern, certainly the worst case number of comparisons is bounded by the length of the pattern, but typically it's not going to be that much. But still, we don't know, so this is what we take as the worst case. Okay? So this is a P times T. And in fact, you can come up with examples where the worst case amount of work in this algorithm is in fact that much. Okay, what's a good example of that? Steve? Stephen?
Well, if your pattern and your text are all just the same character repeated over and over again?
Yeah, let's say the text is all A's and the pattern is all A's. So every place you put down the pattern, you're going to compare, with this algorithm, you're going to compare all the characters in the pattern against the corresponding characters in the text, and then you're going to move it over, you're going to find a match, and you move it over by one, you start again. Now, think about it a little bit. In that very special case, you can come up with a modification of this algorithm, which is much more efficient. But the algorithm generally doesn't know that you're in that case. So, and in fact, in general, we can come up with algorithms that are more efficient than this, and we will. But this algorithm certainly has theta p times t running time, just because now we've seen an actual example or examples that are, we can make them any length we want and have this worst case running time. Okay, so I'm going to rewrite that just a little bit for my next, I'll write it over here. This is p times t. Okay. And just try out some numbers here. If the text, let's say, is 3 billion, that's the length of DNA, although DNA databases are massively larger than just that. The pattern could be in the thousands, so you have thousands of billions because of the multiplication here. That's real money. And if you write this algorithm up, again, this is a very simple thing to code up, you'll try it out on some non-trivial length strings, and really you can feel the time, you can see the time. So that's not desirable. 1973, around about there, maybe a little bit before then, I think the first Knuth Morris Pratt came up with an algorithm that was much more efficient than p times t, did something very non-trivial. They replaced this symbol with this symbol. Okay? Just turn that thing 90 degrees. There's a small transformation. So a very minor operation on the symbols changes the running time from thousands of billions to just billions. Okay? But you can really feel the difference between those two. So Knuth Morris Pratt showed that you can find all occurrences of the pattern inside of a text in time proportional to the length of the pattern plus the length of the text. And as we've said this before, this is linear time. Linear time means that's just proportional to what it takes to read in the data in the first place. You have to spend something on the order of the length of p just to read in the pattern, and something on the order of the length of the t just to read in the text. And yet you can find all the patterns, all the occurrences of patterns in text in that time. That's really quite amazing. Now, the Knuth Morris Pratt algorithm, and since then several others, many others, achieved that running time. And Knuth Morris Pratt is what's often in textbooks. Not this textbook. Strangely, the textbook we're using doesn't talk about pattern matching at all. So I'll put some I have put some notes already on the class website that we can use in place of the textbook, because most algorithm textbooks talk about pattern matching with some approach, usually Knuth Morris Pratt, but this book doesn't at all. Anyway, we aren't going to talk about Knuth Morris Pratt because I think it's a little too complicated. We're going to talk about a simpler approach that I call the Z algorithm. And as I said, I posted notes on the class website about the Z algorithm. So, in fact, the Z algorithm is a little bit more general than pattern matching. The Z algorithm is going to solve a problem which will allow us to do the pattern matching problem in this time bound, but it actually does other things as well. So I have to define what Z is, what Z values are, and then we'll get back to pattern matching, and then we'll go on to look at the Z algorithm itself in detail. So this is a definition. Given a string S, so S is just going to be a generic string. At the moment, I won't tell you whether it's the pattern or the text. But given a string S, Zi of S is defined to be the length, so it's a number, of the longest substring in S, starting at position I, at position I, that matches a prefix of S. Okay? Prefix is a substring at the beginning of a string. Suffix was a substring at the end of the string. We talked about suffixes last time. Now we're talking about prefixes. Okay? So let's just do some examples to make that definition concrete. AA, BC, AA. Example. I'm not going to be able to remember that. AA, BC, AA, BX, AAZ. Okay? Okay, so Z2, I'm going to drop the explicit S in here. It's just extra writing. What is Z2? Just look at the definition. Given a string S, Z, now in this case 2, is the length of the longest substring in S, starting at position 2, that matches a prefix of S. So here's position 2. It matches initially it matches prefix A. It's useful to have two fingers for this on two different hands. So 2 matches 1, but then 3 does not match 2, so Z2 is equal to 1. Right. And what is Z3? 2?
0.
0? I hear 2, I hear 0. What is it?
0.
0. The length of the longest substring of S, starting at position 3, that matches a prefix of S. So you start at position 3. There's 1, 2, 3. I guess I didn't tell you that we're starting indexing at 1. Okay, not at 0. 8, 9, 10, 11. I wouldn't have to even say that except for the fact that you all program in C or some other languages where they start at 0 for some absurd reason. But at any rate, we're starting indexing at 1 because we're at the moment sane. And so position 3 is here, and the substring that starts at 3, the longest substring starting at 3 that matches a prefix, well, it doesn't match. So that's length 0. Okay? Z4 is 0. What about Z5?
3.
Anybody in the back?
3.
3. Okay? Because A matches A matches A, B matches B, but C and X don't match. So that's 3. Okay. Why didn't I talk about Z1, by the way? It's what?
There's no prefix.
No prefix. Or you could say the longest substring that starts here that matches a prefix is itself. Okay, so this is just going to be the length of S, and so it's predictable, it's trivial, it's not interesting. Okay, so we have these definition of what a z-value is. Okay, now let's try to relate this. Ultimately, I'm going to show you an algorithm for computing the z-value for every position. And that algorithm is going to run in time proportional to the length of the string, S. Okay? So it's going to be linear time. In linear time in the length of the string S, we're going to be able to produce the z-values for every position. The question right now is, if you have an algorithm to find all the zi values, how do you use it? The pattern matching question. How do you use the algorithm that has the z algorithms to find all the occurrences of a given pattern inside of a given text? Yeah, Mike?
If you put the pattern before the text, and then you find the z-value of that, and then you would like eliminate certain values that are longer than the pattern. So then only the z-values when it's the same length as the pattern.
That's close. It's close, not quite right. Anybody else have a suggestion? Okay, the suggestion was that you create S equals P followed by T. So it's the pattern concatenated with the text. Okay? And then find all zi values in S. Okay? And any zi, well, you said equal to the length of the pattern. Okay. So this is what was suggested. Zi equal to P identifies an occurrence of P in T. Okay? Is this correct, complete and correct, or? Yeah. Greater than? Alone? Just greater than? Or equal, yeah. Right. So this actually is true that any zi that equals P does identify an occurrence of P, but it doesn't necessarily identify all of them. So you want it to be greater than or equal to P. And you can just sort of see this pictorially or just from the cartoon. If we have here a position where, let's say it's position K, well, position I, zi is equal to the length of P plus 10, something like that. It means that from here, in the length of P, that matches that, because P is at the beginning of S, and then the next 10 characters also match. But the main point, and so zi at that point is bigger than P. But the main point is that the first P characters, the number of characters equal the length of P, definitely also matches P. And so this finds all occurrences. Now, sometimes what people do is, when they think of problems of this type, just to facilitate the algorithm and facilitate the thinking about it, and slightly speeding up things, is that they'll put a character, let's say a $, between the two concatenated strings, where this character is guaranteed not to be in either of these strings. So you put some character that's outside of the normal alphabet that's used in the pattern in the text. So if we're talking about strings of DNA, then that's a 4-letter alphabet, and there are lots of characters you can use. But anyway, you have available to you some character that's not in the normal alphabet that's used. And then, if you did that, how does that change this statement? Well, let's break it down. Is this statement still true? Is this statement still correct? Yeah, it is still correct, but it can be sharpened a little bit, which is it should now just be what you originally suggested, which is that Zi equals P. The point is that nothing in T, this character is not in T, so you can't ever have a position that matches a prefix for more than the length of P, because the comparisons out here would run into comparing that character, and that character is not anywhere in T. So if we put that in there, then we can make this equality. But either way, both statements work. All right. So if I can find all the Z values in time proportional to the length of S, then I can use this idea to find all the occurrences of the pattern P inside of T in time proportional to the length of P plus the length of T. Okay, so if we can find a Z algorithm, if the Z algorithm that's coming up actually finds all the Z values in time proportional to the length of the string that it's operating on, and we use this idea, P followed perhaps by a $sign followed by T, then we can find all occurrences of the pattern inside the text in this time bound. Okay. Now, it'll turn out that the Z algorithm is useful for other applications as well, but this certainly shows that a linear time algorithm to find all the Z values can solve the pattern matching problem in linear time, give a solution that solves the pattern matching in linear time. By the way, what would happen if instead of forming S equals P followed by T, suppose you reversed that and you had S is equal to T followed by P? Would that work for solving the pattern matching problem? No, it won't. So cross that out. It's not symmetric. We're looking for the pattern inside the text, and it works to make the pattern the prefix and not the other way around. Okay, so now I want to show you the actual algorithm that will find the Z values, all the individual Z values, in time proportional to the length of S. And I need some additional notation. So the Z algorithm. Okay, let's say that this is a position where Zi is greater than 0. So what does this mean? It means that starting from position I, there is a string, a substring, that matches a prefix. And how long is it? Well, it's that long. Okay, I don't know how long that is, but that definitely matches a prefix of S. So these two match. So if I give that name alpha, that string inside there, alpha, this is also an occurrence of alpha, right? And by definition, this is the longest substring that starts at position I that matches a prefix. So if this is character X, the next one after that occurrence of alpha is X, what do we know about the character here? It's not X. That's all I can say. I'll call it Y, say, where Y is not equal to X, because this was the longest substring starting at position I that matches a prefix. Okay, so I'm going to have drawings that have little boxes like that to represent the actual substring that matches, and I give that a name of a Z box. Okay. All right, so Z boxes, if we look pictorially at what's happened in the algorithm will have found some of these substrings that match prefixes, and those will define Z boxes. So we'll have pictures that have those little boxes in there, and that's a name. Now, I should have told you that the algorithm is going to compute the ZI values from I equals 2 up to the length of S. So the algorithm compute ZI from I equals 2 to I equals the length of S. So in order. So Z2 followed by Z3 followed by Z4 and so on. All right. So as the algorithm proceeds, it's finding Z values in order, and it's finding Z boxes. And so I want to define a variable, a programming variable that the algorithm uses as the algorithm proceeds. The name of this, let R, that's a variable, be the rightmost position in any Z box found so far. So the algorithm is proceeding. Let's say this is, we're up to this point. If this is the picture of all the Z boxes that have been found so far, this is R. It's the rightmost one. It's the rightmost position of any, the rightmost position that's in any of the Z boxes that we found so far. Then the algorithm might proceed, and it may look at this position, and compute ZK, and see that that defines a Z box that goes out to there, in which case the programming variable R changes from this position to that position. Okay? So R is just, what's the furthest position to the right that is included in any of the Z boxes that we find. And so you can incorporate that into your algorithm. And then L is the left end of the Z box whose right end is R. So in this picture, if we found these two Z boxes, and this is the current R, then this would be the current L. Okay. So the left end. Now, I think at the level that I'm going to be talking about the algorithm, we're not going to need L. But if you're ever going to really implement this algorithm and program it, you'd want to keep alive both an L and an R. So as the algorithm goes along, it finds additional Z boxes, and whatever Z box it finds that defines R, the end of that, the left end of that, defines L. Okay, as the algorithm goes along. So we have those two variables that are being changed as the algorithm goes. Okay, so let's get into the core of the algorithm now that we have our notation set up. The first thing is we want to compute Z2. Okay? And that's going to be done in the most explicit and naive way, direct way. So here we have position 1, here we have position 2. And remember what it is that we're trying to do. We're trying to find the length of the longest substring that begins at position 2 that matches a prefix of the string, S. So we just do the two-fingered approach, which is to look, one finger goes at position 2, one at position 1, and we ask whether those are equal. If they're not equal, then Z2 is equal to 0. But if they are equal, then we move over, and we ask whether the character in my right finger matches the character in my left, and so on. And we keep doing that as long as they keep matching until we find finally a mismatch. Yeah?
The reason you start at 2 instead of like the length of the string pattern, because like if you start at Z2, that's still part of the pattern. There's no point.
Okay. There's no pattern and there's no text. There's only a string S. Okay. We showed over here that if you have an algorithm that can compute Z values, you can then use it to find the all occurrences of a pattern inside of a text. But right now we're just talking abstractly about finding Z values in a string S. Okay, did that answer your question? Okay, so A, B, X. Let's say this is the string, 3, 4, 5, 6. So the two-fingered algorithm at this point, character at position 2 matches the character position 1, and then the character at 3 matches 2, and the character at 4 matches 3, and then the character at 5 does not match 6. So Z2 is equal to 4. Okay, a simple homework exercise is that the value of Z2 is actually equal to the number of identical characters at the beginning of S. You can convince yourself of that you didn't really have to do, well, effectively you are doing it, but you didn't really have to do this two-fingered thing when you want to compute Z2. You can just say, okay, the first character is A, and how many additional characters are equal to A, and that's what Z2 is. You can convince yourself that that's correct. Okay. But certainly, we can always go back to the explicit two-fingered approach of actually looking at the characters. And for any position where we want to compute a Z value, we can always do that. If I want to compute ZK out here, I can always put one finger at K and one finger at 1, and then do those comparisons. But we don't want to do that because, yeah, question?
For that example, is Z2 3 or 4?
3, I'm sorry, yeah. 1, 2, 3. Good. Z2 equals 3. Okay, now how many character comparisons did it take to compute Z2 in worst case? Or what can I say for a bound on the number of character comparisons it takes to compute Z2? Okay, Stephen.
What would be the length of S, because if they're all the same character again?
Yeah, the length of S, all right? Now, the algorithm I'm looking for, the algorithm I'm claiming exists, is going to have a runtime bounded by the proportional to the length of S. And just to compute Z2, we've already used up S. So I'm really cooked, right? What's the answer to that? So in worst case, just to compute Z2, I've had to use a number of character comparisons equal to S, and yet I'm claiming that the whole algorithm will only use a number of character comparisons proportional to S. What can you conclude from those statements? Yeah.
Well, if Z2 is equal to S and they're all the same character, and so you know that the Z value of each one after Z2 is just going to be one less.
Well, that's true, yeah. So you're really looking at it very closely and saying, if we really did spend S on the first, at the beginning, we wouldn't have to spend much for the rest of it because we're pretty much finished. And that's true. We won't even have to be that clever. The only answer I was looking for is, yes, we spent S to compute Z2, but the advertised time bound for the whole algorithm is proportional to S. So I've got several S's left over to use. Okay, but it cannot be that I do this at every position. I can't use the two-fingered approach at every position because if I'm counting S as my worst-case bound for computing each Zi value, then if we do that S times, then we're talking about S squared, not S. Okay, so I better do something that's more clever. So even though the beginnings of the algorithm are very direct, very explicit comparisons, we better be more careful and clever as we go on. All right, so let's just say we have gone on, and we've already computed zk. So we've computed z2, z3, all the way up to zk, and now we're trying to compute zk plus 1. So there's going to be a couple of cases that we're going to look at that are going to relate K and R. So case 1, let me make sure these are the same. I'm using the notation of what's in the notes. Case 1, K is bigger than R. So that means that there's no Z box that goes as far as we're trying to compute ZK. So we've computed ZK minus 1, and we're trying to compute ZK, right? So if K is bigger than R, that means that the rightmost Z box, the Z box that ends farthest to the right, does not go as far as position K. So K is strictly to the right of R. And what we do in that case is explicitly find or compute ZK by the two-fingered algorithm. Finger algorithm. Okay? So in that case, we're back to what we did for Z2. That doesn't look so good because you can't do this at every position because then as I was mentioning, your time bound is going to be S squared, not order S. But anyway, it's certainly clear that when K is bigger than R, if you do the explicit comparison approach, the algorithm is correct because you're just looking directly. There's nothing tricky going on there, so there's no need to worry. That's case 1. Case 2 is that K is less than or equal to R. I draw a picture like that. Here's a Z box that defines R, and we're back looking at position K, and we're trying to compute ZK. One question that often comes up when I start talking about this case, people are a little confused how R got to be, how did R get to be bigger than K? Okay. Well, the point is that R got defined when we were computing Z. What subscript here in terms of our notation that we've been talking about?
L.
It what?
L.
L, yeah. Back when we were computing ZL, we found that the longest substring that begins at position L that matches a prefix went all the way out to R. So we know ZL at that point, but we don't know all these other Z values in between, and then we're going to compute them one at a time. And here we are now looking at ZK, and it hasn't yet caught up to R. So certainly K can be less than or equal to R. Okay, so we're in that case. Let's draw the picture a little bit. This whole string is going to be called alpha. And by definition, there's got to be another alpha at the beginning of the string. This is a substring that matches a prefix, so that we have an alpha both of these places. We've talked about this before. The next character over here is X. Next character over here is Y, where Y does not equal to X. Y is not equal to X, okay? All right, now just to facilitate the argument, I'm going to call the substring inside here beta. So alpha is the whole thing. Okay, alpha is this entire substring, and beta is the substring that begins at K and runs to R. Okay? So beta is the substring beginning at K running to R. And where is another occurrence of beta in this picture? Yeah.
At the end of that alpha at the beginning?
Right, because alpha is equal to alpha, so this has got to be another beta. Okay? And you can figure out, if you're actually trying to program this, you can figure out what this index is. If you know what R is, you know what L is, you know what K is, you can certainly figure out what this index is. Okay, I'm just going to call it K prime without getting into all the messy details of how you would actually compute what K prime is. But it's the beginning of this occurrence of beta where K is the beginning of this occurrence of beta. And we can certainly figure out what K prime is from all the values that are known. All right, so in case 2, I'm claiming that claim well, let me just go to a subcase. Case 2a, zk prime is less than the length of beta. Okay? So starting at k prime, the length of the longest substring that matches, starting at position k prime, that matches a prefix, that length is less than the length of beta. So let's draw that picture. I'll put beta up here. Okay, so this is k prime plus zk prime plus or minus 1. Who knows how to do arithmetic? Anyway, this length here, the length of this thing is zk prime, okay? The length of this is length equals zk prime. Case 2a, claim, in this case, zk equals zk prime. Well, I'll just do very quickly, and I'll come back to this next time. Here's beta. We're looking for the longest substring that starts at position k that matches a prefix. Okay, zk prime has to match a prefix. I mean, whatever this, call it gamma, there has to be an occurrence of gamma there, right? by the definition of zk prime. This is gamma, this is gamma. Let's say this one is, the next character is p. What's the next character over here? Q, not equal to p. Over here, this is beta, so this must be gamma inside there. Okay? What's this next character?
P.
It's p. Okay? So starting from position k, we have a substring, gamma, that matches a prefix. The next character over is p, which we know does not match the next character over because that's q. Q is not equal to p. So there we have explicitly that zk is equal to zk prime. Okay? zk equals zk prime. So in this case 2a, how many character comparisons do we use to compute zk? So the algorithm wants to compute zk. It finds that k is less than or equal to r. It figures out what k prime is. It looks up what k prime is. It knows what the length of beta is. It compares zk prime to the length of beta, finds we're in case 2a, computes zk, concludes zk is equal to zk prime. And how many character comparisons did that use? 0. So it did some arithmetic, but a constant amount of arithmetic independent of what positions we were. It used a lookup, but only one, that's constant. So this is a really good case where we do 0 character comparisons. And if we can do that for every position, then the whole algorithm will run in time 0. But, okay, it won't happen every position. All right, next time we'll finish the algorithm, finish the analysis, et cetera, et cetera.